we'll talk through chapter 1, and we'll try to get as far as we can into chapter 1 in this optional synchronous session. This content will mirror the lecture recordings already provided on Canvas, but I wanted to provide some supplemental information. Okay, so first off, let's just introduce everyone to the central premise of chemistry, the central goal of chemistry. What is the purpose of chemistry? Well, chemistry focuses on the study of matter, its transformations, and the energy changes that accompany those transformations. Now, there's a lot to unpack in that statement. Energy can be defined as the ability to do work or accomplish change. And matter is defined as anything that takes up space, has volume, and anything that has mass. We can describe matter as being composed of fundamental particles called atoms. So when we view solid, liquid, and gaseous matter, the various components of the world around us, as chemists, we really think about matter as a collection of smaller particles known as atoms. Now, why is this important? What is the benefit of looking at the world from this perspective? Well, the main purpose behind this atomic view of matter is that we can begin to understand how the composition of matter determines the properties of matter. Atoms of different elements with different symbols have different properties. Further, when we start to bond atoms together to form more complex structures called molecules, we can begin to see how the properties and function of a molecule depends on its composition. The atoms that make up matter determine the properties of matter. An example that we've encountered in our day-to-day lives is hydrogen peroxide, H2O2, is a disinfectant. It is not safe to drink, while water, H2O, is perfectly safe to drink. As we notice, the composition of matter, the exact atoms bonded together to make hydrogen peroxide versus the exact atoms bonded together to make water, directly determine the properties. So by studying the composition of matter, to understand the properties of matter. So that's my essential summary of the goal and sort of the ethos behind chemistry. We aim to study matter and begin to understand how the composition of matter determines the properties of matter. Does that introduction to chemistry make sense to everyone? By understanding and by studying matter, we can begin to prepare things with divine properties, and we can begin to start to explain the behavior of the world around us. Now, this is a bit of a broad view of chemistry. We'll talk about components of this discussion in later lectures. So, when we start thinking about practicing chemistry, a central sort of tenet to the practice of science and sort of this practice of observing and beginning to explain and rationalize the world around us is the scientific method. And the scientific method has the following tenets. Science is based on observations. These observations can be either collected data that we call quantitative observations or descriptions of phenomena that we call qualitative. Observations do not attempt to explain the collected data or phenomena. They're just collected data or descriptions. So let's engage in an exercise in observation. Let's try to observe a system and write down what we observe. So in this case, we have a balloon. In the first case, the balloon is at room temperature, which is about 25 degrees Celsius. In the second case, we have a balloon that's immersed in ice, which is at about 0 degrees Celsius. Now let's practice taking some observations. What do we observe about the balloon when it's in ice? What do we observe about the balloon when it's at room temperature? What do we observe? Would anyone like to share some observations?
I will.
Sure, please go ahead.
When it's on ice, the balloon is on ice, the molecules constrict and get smaller. Thus, the balloon is smaller.
Sure. So our observation in this case would be that the balloon is smaller. And I notice you're beginning to start to explain and propose a hypothesis for why the balloon is smaller. And that's good to see. We'll actually talk about that in the next part. So we've made an observation, the balloon is smaller when it's on ice. And in addition to making a hypothesis, if we take a large number of observations, if we begin to collect observations and we study gases at different temperatures for a range of systems, we can begin to compile those observations together. And a series of similar observations for a set of phenomena leads to development of what's known as a scientific law. And scientific laws provide a summary of past observations and provide a prediction of future observations for a system. So if from our observations of gases and how their volume changes with temperature, we can develop and propose a scientific law. In this case, the most appropriate law that describes the behavior of this balloon at different temperature would be Charles' law, which states as the temperature of a gas decreases, the volume of a gas decreases. And laws can be both qualitative and quantitative. Now, the key feature of a scientific law is by amassing all of these observations, we can describe a range of systems, and we have a substantial amount of predictive power. We can predict how a gas would behave at different temperatures using this scientific law. Does everyone understand this idea of observations and scientific laws? So observations are a collection of data or descriptions of the world around us, while a scientific law is a culmination and a summary of observations that has predictive power. So, as we've alluded to, from our observations, we can also formulate what's known as a hypothesis. A hypothesis is an explanation for the collected observations. A hypothesis provides predictive power and it's testable via experimentation. So that begs the question then, well, what is an experiment? An experiment is a carefully designed procedure designed to refute aspects of a hypothesis or provide supporting evidence for that hypothesis. Now, a hypothesis can be revised to account for collected data and observations, or it can be discarded if it cannot be reconciled with our collected observations or collected data. Now, if a hypothesis has been tested and challenged extensively with experiments, and there's a large amount of supporting evidence for that hypothesis, a well-supported hypothesis becomes the basis for what's known as a theory. A theory, quite simply, is a model for the way that nature is that tries to explain what nature does and why. A theory serves to explain natural laws and observations. Here's an example. So we can explain gas behavior using kinetic molecular theory, which describes gases as a collection of moving particles. So we can explain gas behavior using kinetic molecular theory. For example, the balloon at room temperature, we can view the particles of gas as moving quite rapidly and pushing against the walls of the balloon with a large amount of force. At low temperatures, there's less molecular motion, and as a result, the gas molecules push with less force against the outside of the balloon, and the balloon shrinks in volume. We have used a theory to explain the behavior of gases, predict the behavior of gases, and rationalize the natural world and the behavior of the natural world. And this is really powerful because it allows us to predict the behavior of the world around us. Does this idea of the scientific method make sense to everyone? Okay, let's keep going now, and let's talk about how numbers are handled in science. Well, the centerpiece of processing large and small numbers in science is scientific notation. So we know science is based on observations, and one way that we take observations is by collecting data, by taking measurements, using tools called instruments. A classic example of an instrument would be a ruler, for example. Now, each measurement has a number and a unit. So 10 so we'd have 10 meters. So when handling numbers in science, we often deal with very large or very small numbers. So we use scientific notation. When we're talking about atoms, they're very small. When we talk about groups of atoms, that's a very large number. So in order to handle these very large and very small numbers, we use scientific notation. So scientific notation is the form blank times 10 to the n, where blank must be a number greater than or equal to 1 and less than 10. When we talk about rules for our exponent in scientific notation, there are a few guidelines we have to keep in mind. Your exponent n can be any whole number power, no decimals, and n can be negative or positive to describe very small and very large numbers respectively. So let's look at some examples of numbers that are written reasonably in scientific notation and numbers that are written unreasonably. So if we have 0.0935, if we rewrote this as 9.35 times 10 to the negative second, let's check to make sure this number is written correctly in scientific notation. First, 9.35 is less than 10 and greater than or equal to 1. And our exponent, n, is a whole number. There's no decimals here. So this number is fully and properly written in scientific notation. So let's look at another example. If we have 1037, or let's do 3045, we can write this as 3.045 times 10 to the third. Again, 3.045 is greater than or equal to 1 and less than 10, and this number 3 is a whole number. Let's look at some examples of numbers that are incorrectly written in scientific notation. So for example, 10 times 10 to the fourth. What's a problem with this number as written? What's an issue with this number as written? What do we think? Is this number written reasonably in scientific notation, or is there an issue with this number?
Number has to be less than 10.
Exactly right. So 10 is equal to 10. So this is not a valid base number to use when writing numbers in scientific notation. We can rewrite this as 1 times 10 to the fifth, and then everything would be perfectly fine. Let's look at another example. 0.945 times 10 to the third. Is this number reasonable in scientific notation? Is there a problem with this number as
That number is not reasonable because it's less than 1.
exactly right? 0.945 is less than 1, so it's not a valid number when written in scientific notation. We can rewrite this number as 9.45 times 10 to the second. In that case, we now have a perfectly valid number as our base numbers between 1 and 10, and our exponent's a whole number. Now, I haven't ever seen students do this, but it's important to note that if we have 3.45 times 10 to the 0.5, what's wrong with this number if we're thinking about scientific notation? Is there an issue with this number as written? The exponent's a decimal, exactly right. And I haven't ever seen students do this, but it's important to bring up the exponent must be a whole number. So let's talk a little bit now about exponents, and let's talk about how to handle exponents. So an exponent has two parts. It has what's known as the base, and it has an exponent term, n. So to expand out an exponent, you multiply the base by itself a total of n times. So 10 to the second, we'd write 10 times itself 2 times. That gives us 100. Now, there's a trick when you're dealing with powers of 10. When you're dealing with powers of 10 and multiplying by powers of 10, you move the decimal point n spaces to the right if n is positive. So for example, if we have 10 to the 7th, we can write this as 1.0 times 10 to the 7th. We now have a decimal point. So we can take our decimal point, and because we're multiplying by a positive exponent, we're going to move our decimal point 7 spaces to the right. So let's write that out. 1, 2, 3, 4, 5, 6, 7. And each time we're going to put a placeholder 0. So 1, no placeholder 0. 2, now we put a placeholder. 3, placeholder. 4, placeholder. 5, placeholder. 6, placeholder. 7, placeholder. So that gives us 10 million. Does this example of multiplying by positive exponents, positive powers of 10, make sense to everyone? Okay, so let's talk about negative exponents, and this is important. We can write negative exponents as dividing by a positive exponent. You can move any exponent from the numerator to the denominator just by changing the sign. So 10 to the negative third is the same as writing 1 over 10 to the third. In other words, 1 over 1,000, which is 0.001. Now, just like with positive powers of 10, there's a trick for multiplying by negative powers of 10. For powers of 10, you move the decimal point n spaces to the left if n is negative. So for example, in this case, we have 10 to the negative fifth that we can write as 1.0 times 10 to the negative fifth. And now following our rules, we're going to move our decimal point, in this case, 5 spaces to the left because we're multiplying by 10 to the negative fifth. 1, 2, placeholder 0, 3, placeholder 0, 4, placeholder 0, 5, placeholder 0. That gives us 0.00001. Does this idea of multiplying by positive and negative exponents make sense? Are there any questions I can address? If we don't have any questions, let's keep going then. And let's talk about how to convert numbers into scientific notation. So when we're writing numbers in scientific notation, you write the number, placing a decimal point at the end if there is no decimal point. So we have blank times 10 to the n. So let's look at a number 4,057. Okay, so we write our number, we put a decimal point at the end. It's our first step. Now, from here, you move the decimal point until the number is greater than or equal to 1 and less than 10. So I move my decimal point once, I get 405. Is 405 between 1 and 10? Is 405 between 1 and... No, so we have to move our decimal point once more. That gives us 40.57. Okay, we're still not between 1 and 10, so one more gives us 4.057. So we took 4,057 and we moved our decimal point over 3 spaces to give us 4.057. Now we count how many places the decimal point was moved and if it was moved to the left or to the right. Okay, so in this case, we moved our decimal point 3 spaces to the left. I'm going to write that down. Okay, so when you're writing your exponent, we've counted that we moved our decimal point 3 spaces to the left. 1, 2, 3. So then our exponent n is positive and equal to the number of spaces we moved our decimal point to the left. N is positive if your base number is greater than 1. So in this case, what value would we put for n? What is our exponent if we moved our decimal point 3 spaces to the left? What is the value of our, what's the value of our exponent n? It would be positive 3 in this case, following our rules, because n is the number of spaces that we moved our decimal point to the left. So that gives us 4.057 times 10 to the third. And we can check our work, actually, by multiplying things out. So to check that we've done everything correctly, if we multiply 4.057 by 10 to the third, 3, we move our decimal point 3 spaces to the right, and that gives us 4,057. So this is a way to check your work that helps you verify that you've correctly converted your number into scientific notation. Let's look at an example where we have a negative exponent. Suppose we have 0.000659. So in this case, we have a number that's clearly less than 1. We move our decimal point until we get a number between 1 and 10. That requires moving our decimal point a total of 1, 2, 3, 4 spaces. And it's 4 spaces in this case. To the right. So that gives us 6.59. And in this case, because our number is less than 1, and because we moved our decimal point 4 spaces to the right, our exponent n is -1 times the number of spaces moved to the right. In this case, -4. So our final value would be 6.59 times 10 to the -4th. And we can check our work once again by multiplying out and expanding out our number into a decimal. So 6.59 times 10 to the -4th. We move our decimal point 1, 2, 3, 4. That gives us 0.000659. Does this make sense to everyone? Does this process of converting numbers into scientific notation make sense? Okay, so I'm going to do some examples and then we're going to work on some examples as a class. So if we're asked to convert the following numbers to scientific notation, so we have 4,534. So I put the decimal point at the end. I have to move my decimal point 1, 2, 3 spaces to the left. That gives me 4.534. Because I moved my decimal point 3 spaces to the left, my exponent would be 10 to the +3rd. Does this example make sense to everyone? Okay, let's look at what happens when we have a small number, 0.00342001. To get a number between 1 and 10, we move our decimal point, in this case 3 spaces, to the right. That in turn gives us 3.4201 times 10 to the -3rd. Does this second example make sense to everyone? Perfect. So then, let's work on the following examples. So let's work on these examples for about 2 to 3 minutes. And I'd like students to share their proposed responses as you convert these numbers into scientific notation.
Would you like us to annotate?
You can annotate or you can share your responses verbally or in the chat. Either would work in this case. Yep, so they converted the top number into 3.7 times 10 to the negative second. So let's talk a little bit about that then. So we have 0.037. So to convert this to a number between 1 and 10, we move our decimal point 2 spaces to the right. That in turn gives us 3.7 times 10 to the negative second. To verify that we've done this conversion correctly, I'm just going to show what happens if we multiply things out. We multiply things out, we get 0.037. So we've checked our work. Would anyone like to propose a response to convert the second number into scientific notation?
You can move the decimal point to the left once, and it would be 1.5607 times 10.
Yep, exactly right. So we have 1.5607. To get a number between 1 and 10, we move our decimal point 1 space to the left. That gives us 1.5607 times 10, or times 10 to the first. Does that make sense? Any questions on these examples? If not, let's keep going now. And let's do some quick practice converting numbers into decimals. Suppose we wanted to convert the following number written in scientific notation or exponent form into a decimal. So in this case, if we have 3.70 times 10 to the fourth, first thing, we write out our decimal point. And then in this case, because we have a positive exponent, we move our decimal point 4 spaces to the right to give us 37,000. Now in the second case, we have a number that's not written out in scientific notation, but nonetheless can be converted into a fully written decimal. You often see these kinds of operations when you're doing unit-unit conversions and you have a decimal multiplied by some power of 10. So if we have 0.105 times 10 to the negative second, our first step is to write out our decimal, and then we move our decimal n spaces to the left because we have a negative exponent. So because our exponent is -2, we move our decimal point 2 spaces to the left, and that gives us 0.00105. Does this make sense to everyone? Perfect. So let's try to apply what we've learned to the following examples, and let's try to convert the following numbers into a decimal. So let's work on the following 2 examples for about 2 to 3 minutes, and I'd like students to annotate their responses, or you can share your responses in the chat or verbally. Or if you have any questions, of course, don't hesitate to ask them in the chat or verbally. So would anyone like to share their responses for either of these 2 questions?
Sure, I will
Okay, please go ahead.
take a stab at it. Why not, huh? All right, let's see. Sorry, it's big.
No worries.
There you go.
So we have a proposed response of 4,350. So let's take a look at this problem now. So if we have 0.00435 times 10 to the 6th, so we write out our decimal. And now we move our decimal point, in this case, n spaces to the right. In this case, 6 spaces. 1, 2, 3, 4, 5, 6, placeholder 0, and that gives us 4,350. Exactly right. Perfect. So, would anyone like to share their response for the second problem? Does anyone have a proposed response for the second problem?
I have a question for the second problem.
Yes, please go ahead.
Where it says times 1 over 10 to the third power, can't you
Yeah.
convert that to 10 to the power of -3?
Exactly right. We can move any exponent from the denominator to the numerator and vice versa just by changing its power. So 1 over 10 to the third is equivalent to 10 to the -3rd. Exactly right. And from that, you're able to, in turn, simplify this problem into a little bit of a nicer form. And now once we have this set up, we know how to multiply by negative powers of 10. And so we can move our decimal point 1, 2, 3 spaces to the left because we're multiplying by 10 to the -3rd. And that gives us 20.190. Do these problems make sense to everyone? Is this making a little bit more sense? Okay, so let's keep going now and let's talk a little bit about units of measurement. So when we think about a number doesn't have as a lot of meaning in our physical world without a corresponding unit. Units serve to provide meaning to numbers by indicating what you are measuring and what standard unit of measurement you are using. So for example, 10 what? That's not very descriptive. 10 meters, we're describing a unit of length, and our standard unit of measurement is meters. Now, the United States commonly uses the English system of measurement, but the sciences overwhelmingly use the metric system. And this interface between units and the importance of units comes up a lot in day-to-day lives, and it's especially prevalent in healthcare settings where we still end up measuring weights in pounds, but doing calculations in grams or kilograms for dosages. So one example to really illustrate the importance of properly writing down, properly noting units, and being able to identify what each unit is representing is there was an example here where a toddler was brought in for an eye infection. They listed a weight of 25 kilograms rather than the true weight of 25 pounds. And since dosages are calculated based on the patient's weight in kilograms, they recorded twice the weight by mislabeling the units, and they gave twice the recommended dosage. In this case, it didn't have a particularly dangerous effect, but for many medications, properly calculating the dosage from the patient weight is critical. So units matter, and we deal with units a lot in our day-to-day practice. I just thought this was an interesting example of how units can pop up in day-to-day healthcare practice. So when we talk about units, it's important to be able to convert between units through the process of unit conversion. Now, This is where the metric system really shines. The metric system is based on powers of 10, making scientific notation especially useful. So the metric system starts and really builds all of its units from a series of fundamental base units. Distance is described with meters, volume with liters, mass, grams, time, seconds, temperature, kelvins. Now, when we want to indicate large or small quantities of a unit, the metric system uses common prefixes, each with a unique symbol. This prefix modifies the base unit to give what's known as a prefix unit. So for example, if we have a meter, a decimeter, the deci prefix is telling us we have 10 to the negative first meter or 0.1 meter. As you see, when we add the prefix, we're now describing a smaller or larger quantity of our base unit. Does this picture help everyone see what a prefix unit is doing? A meter is our base unit. The prefix modifies the base unit to give a prefix unit, which represents a small or large quantity of our base unit. So for example, each of these prefixes corresponds to a power of 10 amount of our base unit. A centimeter, 10 to the negative second meter. A kilogram corresponds to 10 to the third or 1,000 grams. A milliliter corresponds to 10 to the negative third liter, and so forth. Each time the prefix modifies the base unit to give a prefix unit, which represents a small or large amount of our base unit. Now, the beautiful thing about each of these prefixes is they're based on powers of 10. So you're responsible for memorizing the prefixes and memorizing each of these powers of 10. The reason for that is because when you want to convert a prefix unit to a base unit, this is where it's really easy. All you have to do is replace the prefix with the power of 10. So 657 millimeters, the milli prefix corresponds to 10 to the negative third. So if I wanted to convert millimeter to meter, all I have to do is replace the milli prefix with 10 to the negative third. So that would give me 0.657 meters. Does this process, converting from prefix to base units, make sense to everyone? All you do is replace the prefix with the corresponding power of 10. So let's look at this second example. So we have 457 kilograms. If we're converting from kilograms to grams, what does the kilo prefix represent?
10 to the third.
10 to the third, exactly right. So we replace the kilo prefix with 10 to the third, and that gives us 457 times 10 to the third, that we can write as 4.5 second times 10 to the second times 10 to the third, which we can write as 4.57 times 10 to the fifth grams. Does this example of prefix to base unit metric conversions make sense?
sorry, where'd you get the 4.75 times 10 to the second from?
So I took 457 and I just converted it to scientific notation by moving my decimal point
Oh, got it, I see.
two spaces. Any other questions I can address? Okay, so let's now talk about the fundamental idea behind unit conversions. So different units and numbers can describe the same quantity. So does everyone see this red line here? This red line is representing a distance, right? And we can measure that distance in centimeters or inches, right? Centimeters and inches both describe distance. So as we can see, if we measure this same quantity of distance, this same amount, same length, we see that in the centimeter ruler, we get 2.54 centimeters. And that distance corresponds in our inch ruler to 1 inch. So we've established that these two quantities are equal. 2.54 centimeters is the same distance as 1 inch, right? Does everyone see that on the ruler? Does that idea make sense? Okay, so we can write unit conversion factors as a ratio of two equal quantities. So 2.54 centimeters equals 1 inch. We can divide both sides by 1 inch, and that gives us 2.54 centimeters per inch is equal to 1. Or we can write the inverse, where 1 inch over 2.54 centimeters are equal to 1. Both of these ratios are known as unit conversion factors. They're a ratio of equal quantities. Does that make sense? Okay, so now we can multiply any quantity by 1 and the quantity is unchanged. The units and number change when you convert between different units. This is important because when multiplying and dividing by conversion factors, the units cancel just like normal numbers. So for example, if we're trying to convert 2 inches into centimeters, we would take our 2 inches and multiply it by our conversion factor, which is 2.54 centimeters per inches. As you can see, just like 7 over 7 cancels because we have the same number in the numerator and denominator, inches over inches cancel there because they're identical units. Thus, we're left with units of centimeters, and we can conclude 2 inches are equal to 5.08 centimeters. We have not changed the quantity of distance that we're measuring. We've just changed the number and unit describing that distance. Does that make sense to everyone? Okay, so one thing I want to make clear is when you're doing unit conversions, you want to make sure that the units cancel and make sure you write out all of the units associated with the number. This comes up when you have square or cubic units. So just make sure you write out the full set of units before doing a unit conversion. So let's do a step-by-step example where we convert from one unit of measurement to another unit of measurement. So in this case, we're asked how many milligrams are in 3.46 times 10 to the first kilograms. So this is my procedural method that I use for unit conversions. First, you indicate what units you're starting from. In this case, we're starting from kilograms. We indicate next what units you're trying to convert to. We're trying to go to milligrams. So in our map, we want to go from kilograms to milligrams. And I always tell students, it's difficult to go directly from prefix to prefix units. It's very error prone unless you're experienced. So instead, because we know that we can go to the base unit quite easily, it's easy to go through the base unit when doing these prefix to prefix conversions. The conversion factors are easy to write from the table, and it's easy to do these kinds of stepwise conversions if you go through the base unit. Okay, so our next step, now that we have our unit conversion map, is to identify a conversion factor containing the desired base unit and the starting prefix unit. So we want to go from kilogram to gram. Okay, we know that we can write out a conversion factor by taking the prefix and converting it to a power of 10. So 1 kilogram, what does the kilo prefix correspond to? So if we go all the way to our table, the kilo prefix corresponds to what power of 10?
3.
Yep, exactly right. So then we know 1 kilogram corresponds to 10 to the third gram. So if we want to go from kilogram to gram, the units we want to go to need to be on top in our numerator, and the unit we want to cancel in this case should be on the bottom in the denominator. So then when we write our conversion factor, we're going to write our conversion factor so our desired units are in the numerator, so grams are on top, and the undesired units are in the denominator. Kilograms are on the bottom. Now, all we have to do is execute. So if we have our starting number of 3.46 times 10 to the first kilogram, we want to go from kilogram to gram. Our conversion factor will have grams on top, so we have 10 to the third grams, and we'll have kilograms on bottom, so kilograms cancel. That in turn gives us 3.46 times 10 to the fourth grams. Does the first step in this unit conversion scheme make sense to everyone? So now that we have converted from kilogram to gram, we've checked that off. We now need to go from gram to milligram. So we have 3.46 times 10 to the fourth gram. And if we want to convert from gram to milligram, again, we have to generate a conversion factor. So again, we write out an equality. 1 milligram corresponds to how many grams? 1 milligram corresponds to how many grams? What does the milli prefix correspond to? So let's find it. So what power of 10 does the milli prefix correspond to?
10 to the negative 3.
Yep, exactly right. So then let's plug in that power of 10. And now this time, if we're going from gram to milligram, units of milligrams will be on top, units of grams will be on the bottom. Okay, so we have 3.46 times 10 to the fourth grams. And if we're going from grams to milligrams, milligrams should be on top, grams should be on the bottom. So we're going to put 1 milligram on top, and then we put our 10 to the negative third gram on the bottom. As a general rule, you always keep the power of 10 with the base unit in this method. Grams cancel, and so we have 3.46 times 10 to the fourth over 10 to the negative third milligram that we can write as 3.46 times 10 to the fourth times 10 to the third milligram. And as a general rule, when you multiply exponents, all you have to do is add the exponents together if the base is the same. So that in turn gives us 3.46 times 10 to the seventh milligrams. Does that make sense to everyone? Does that process make sense?
Professor, I'm still hitting a wall with how you're getting, because it was the -3. So we're just pretty much dropping off the negative, leaving it up there,
Yes.
and then adding the two.
So you can move any negative exponent to a positive exponent by changing the sign. So if you want to move something from the denominator to the numerator, all you have to do is change the sign. So 1 over 10 to the negative third corresponds to 10 to the third.
Okay, so that's just a simplified version of everything you just said.
Yes,
Okay,
exactly.
perfect.
And then once you have your two positive exponents, you just add them together. Did that answer your question?
It did indeed, thank you.
Perfect. Now, just to show everyone what this would look like as a one-line conversion, if we start with 3.46 times 10 to the first kilogram, and we want to convert this to milligrams, we go through grams. So we have 3.46 times 10 to the first kilogram. We know 1 kilogram corresponds to 10 to the third gram, and we know 1 milligram corresponds to 10 to the negative third gram. So for our first conversion, when we go from kilograms to grams, we'll have grams on top. So we have 10 to the third grams on top, and then the kilograms are on bottom. So we have our 1 kilogram on the bottom. Kilograms cancel, we're doing good. To go from grams to milligrams, milligrams will be on top, grams will be on the bottom. So we put 1 milligram on top, we put 10 to the negative third gram on the bottom. And now when you're adding powers of 10, when you multiply powers of 10, you can simply add the exponents together. So 1 plus 3. When you're dividing by powers of 10, you subtract the exponent. So we have 1 times 10 to the first times 10 to the third, 1 plus 3. We're dividing by 10 to the negative third, so we subtract -3, which turns into +3. So that gives us 3.46 times 10 to the seventh milligrams. Does that process make sense to everyone? So let's do one more representative example. In this case, we're asked how many nanometers are in 4.5 times 10 to the fourth picometer. So we know if we have 4.5 times 10 to the fourth picometer, that's our starting unit. We're trying to go from picometer to nanometer. And our intermediate unit, our base unit, our shared base unit between picometers and nanometers will be our base unit of meters. So with this established, now what we're going to do is we're going to convert from picometer to meter and then from meter to nanometer. So let's write out some equalities. 1 picometer, the pico prefix corresponds to 10 to the negative 12. 1 nanometer, the nano prefix corresponds to 10 to the negative 9th meter. So setting this up now, we have 4.5 times 10 to the fourth picometer. And we know that to go from picometer to meter, we'd want units of meters on top. So we're going to put our 10 to the negative 12th meters on top and our picometers on the bottom. So 1 picometer on the bottom. To go from meter to nanometer, we're going to put nanometers on top and we'll put meters on the bottom. So we have 1 nanometer per 10 to the negative 9th meter. Picometers cancel, meters cancel, and we're left with 4.5 times 10 to the 4th times 10 to the negative 12th times 1 over 10 to the negative 9th nanometer, which we can write as 10 to the 4 minus 12 minus negative 9, which gives us plus 9, which gives us 10 to the 1st. So we can rewrite this as 4.5 times 10 to the 1st nanometers. Does this example make sense to everyone? Any questions on this example? Okay, let's do one more representative example. We're asked how many centimeters are in 0.5 times 10 to the negative 3rd millimeters. So in this case, we're trying to go from millimeters to centimeters. So what's the common unit between millimeters and centimeters? What's our shared unit? Our shared unit would be meters. Exactly. So then, with that shared unit established, we're going to set up our unit conversion. So we have 0.5 times 10 to the negative 3rd millimeters. To go from millimeters to meters, we need to write out our equalities. So we know 1 millimeter corresponds to 10 to the negative 3rd meter. We're going from millimeter to meter. We're going to put meters on top. So we have 10 to the negative 3rd meter per 1 millimeter. Okay, millimeters cancel. We're on the right track. To go from meters to centimeters, we know 1 centimeter corresponds to 10 to the negative 2nd meter. So from here, to go from meter to centimeters, we're going to put centimeters on top. So we have 10 to the negative 2nd meter per 1 centimeter. That's not right because centimeters need to be on top. So we're going to put 1 centimeter over 10 to the negative 2nd meter. Now our units cancel. So with that full setup, we've canceled all of our units. And now all we have to do is compute out our powers of 10. So we have 0.5 times 10 to the negative 3rd times 10 to the negative 3rd times 1 over 10 to the negative 2nd. So that gives us 0.5 times 10 to the negative 3 minus negative 2, which is plus 2. So that gives us 0.5 times 10 to the negative 4th centimeter, which we can rewrite as 5 times 10 to the negative 5th centimeter. Does this example make sense to everyone? Okay, so just to make sure students have the opportunity to attempt a problem in lecture, and just to make sure everyone's comfortable with this idea, let's take about 3 to 4 minutes to work through the following example, and then we'll come together as a group to discuss in about 3 to 4 minutes. If students would like to share their proposed responses, any questions that they have, or if they'd like to annotate their proposed solution, don't be shy to share your responses on the class whiteboard. So let's work through this example. You may want to share your proposed solution map. And I really just want to give everyone the opportunity to ask questions in the context of solving a problem and just to make sure everyone's comfortable with this process. So would anyone like to try to share an annotation or their thoughts as they work through this problem? Or does anyone have a question? Would anyone have, does anyone have a proposal for the response from this unit conversion? How are we doing in terms of time as we work through this example? Would everyone like some more time, or would you like to discuss? These sessions are really for your benefit, so whatever you would prefer. I'd be happy to discuss this problem now if you'd prefer, or if you'd like to spend some more time on it and I can address your questions. You can even annotate your proposed responses, and I'd be happy to provide input as well.
Professor, can I ask a question real quick?
Yes, please go ahead.
Okay, seeing as that we are going from milliliter to liter to the UL,
Yes,
um,
microliters, yep.
perfect. But the first thing that stumps me is the fact that it's a whole number. So I know I already have to move the decimal to make it between numbers of 1 to 10.
When you're doing unit conversions, you don't have to convert it to scientific notation immediately. You can just start with the 1, 2, 3, set it up from there, and then handle your number at the end.
Oh, okay, perfect. Thank you. I think that's what was throwing me off.
And I think in that way, if you enter it all into your calculator actually can process out all of the powers of 10, and that may save you some time in the computation. Especially for these problems, if your setup's good, then you can resolve the numbers at the end once you have all of the conversion factors lined up. Did that answer your question?
Yes, it did. Thank you.
Perfect. Are there any other proposed responses? Would you like us to discuss the question now? I just want to make sure I'm pacing things out so that the class has an opportunity to work on the problem, or if they're ready to discuss, or if they'd like some more guidance and clarification, I'd be happy to provide that. So let's discuss. So we in our unit conversion map, we're starting from milliliters, we're trying to go to microliters. So in this case, we're starting with 153 milliliters. We're going to go from milliliters to microliters through units of liters. Out our equalities. 1 milliliter corresponds to 10 to the negative third liter. 1 microliter corresponds to 10 to the negative sixth liter. So we're going to take our 153 milliliters. And our first step is so if we're going from milliliters to liters, units of liters will be on top. So we have 10 to the negative third liter per 1 milliliter. Milliliters cancel. To go from liters to microliters, microliters will be on top. So we put the 1 microliter on top, and then we put the units of liters on the bottom, which is 10 to the negative 6 liters. Liters cancel, and now we're left with 153 times 10 to the negative third times 1 over 10 to the negative sixth microliters. And that gives us 153 times 10 to the negative third times 10 to the sixth microliters, which gives us 153 times 10 to the third microliters, which you can rewrite as 153 times 10 to the fifth microliters. Does this example make a little bit more sense to everyone? Any questions on this example? Okay, so what we're going to do is we're going to shift gears a little bit as we've done a problem solving session. And I want to make sure we have enough time to talk a little bit about the labs. You can look at the labs and you can get some questions answered about the laboratories. So I'd like for us to talk about the first lab today and talk a little bit about what you're going to be doing in today's lab. Does to everyone what we're doing now? So what I'm going to do is I'm just going to archive